Hi, welcome to Module 7 for weather and forecasting. We're going to start talking about atmospheric global circulation of air masses and some of those natural things. And what we're talking about in this case, or to start with, we're going to talk about global scale circulation. So things taking place over thousands of kilometers in a synoptic scale. So talking about large scale. When we talk about large scale, we're talking about mesoscales. And these are things that are often at least 100 kilometers, 100 square kilometers or greater. Stuff that's under 100 square kilometers, we call microscales in there. So we have two different scale sets, mesoscales and microscales. Now, microscales we've talked about already when we talked about things like mountain and valley breezes and sea breeze versus land breeze. So those sorts of things are microscale climate actions. And in this case, we're going to be talking about mesoscale, large scale. The first part that we're going to begin talking about is what's called the Hadley scale. And this is the natural movement or progression of air mass from places of energy surplus, where there's a lot of heat, to places where there's energy deficit. And the first proposed model was what's called the single cell model. And this is where energy that was very intense at the equator would need to move northward and southward towards the poles. The problem with this model is that it didn't work when you looked at the actual globe. So this is the original Hadley scale. When you looked at the actual globe, we had intense heat at the equatorial zone, which means that there was extra sunlight, and that extra sunlight was heating up the air masses, and that heated air was rising, right? And we can see that. If I look at places near the equatorial zone, we will see a huge amount of cloud cover, and that means condensation. So I'll see a lot of rainfall. And then if we take a look at the belt where the Earth's rainforests exist, it's right along the equatorial zone. But under the original Hadley scale model, it said that that energy would then move in the upper parts of the atmosphere, what we call air aloft. And by upper parts of the atmosphere, we're in the troposphere. So we're still in the lowest parts of the atmosphere. We're within our 30,000 meter mark, right? So we're right in the lowest parts of our atmosphere in the troposphere. And we're talking about air aloft within that troposphere. And it would move towards the poles. The catch is, when we looked at the actual model of air masses, we found it didn't do that. The air would cool off too quickly and sink well before it ever hit the North Pole on our latitude. So this brings me to some latitude lines and about average. So this is my equator area. So if I had my little draw-in, this would be my equator on my latitude belt. This region here is about 30 degrees north latitude. This is about 30 degrees south latitude. And then over here is about 60 degrees south latitude. And up here is about 60 degrees north latitude. And then here is 90 degrees north latitude. And down here is 90 degrees south latitude. So what we're talking about in this model has specific latitude regions, more or less. And it shifts north and south, which brings me things like monsoon seasons. Monsoon meaning rainy season or rainy time. Monsoon by definition actually means wind shift, but that wind shift often brings the rain. So we synonymously put it with the word monsoon. And what we found is that we have a natural cell, it's called the Hadley cell, and it happens to converge on the ITCZ, and this is another key word. The ITCZ is the intertropical convergence zone. It's a term that you guys are going to need to know, one of those definitions that I'll throw at you with multiple choice questions, so you know your ITCZ zone. It means air in the intertropical convergence zone is rising, and it's raining out, and then that dry air is moving north and south, right? So it's diverging, and it cools off and it sinks. And this creates high pressure because it's sinking air mass, right? And it's creating high pressure on the surface. And this is called the subtropic high. And if I looked at my Earth maps, which we will in a couple slides, I will see that my zones of deserts tend to be around 30 degrees north latitude and 30 degrees south latitude. And these are on my subtropic high belt. From there, that air then diverges again, and some of it goes back towards the intertropical convergence zone, and some of it moves north and southward, like down here, right? Moves north and southward towards what we call the subpolar low, and that location ends the Ferrel cell. So we have Hadley cell, Ferrel cell. From there, the air then rises again. And if I look at my latitude belts and I look at my Earth ecosystems again, I will see that there's another what we call cold weather rainforest. This is what we call our Ortega-style rainforests along the 60 and 60 mark. And these are places like the Tongass National Forest along the coastlines of Vancouver and southern Alaska. That is a cold weather rainforest. It rains more times in the year and it's under low pressure. It's often a very rainy, wet place along the subtropic low. And in this zone, the air rises up again and it diverges aloft. And some of it rotates back down within the Ferrel cell, and some of it rotates into what's called the polar cell, which is the northernmost cell, which cools off and sinks right around 90 degrees north latitude and 90 degrees south latitude. And this is my polar cell. And this polar cell zone is the reason why tundras are dry. There's virtually no rainfall on my north and south pole locations. And so these are incredibly dry, cold desert locations is the way that we would describe them, dry, cold desert. And these are on my polar north and south caps. And this ends my polar cell. So the next few slides, and I might skip them, goes through just defining these, but I really wanted to do it based on this image because I felt like the image really encapsulates it. So please feel free to go through and read all those terms on those slides, but you're going to see me jump ahead about 5 slides now. Really quick, before I jump ahead, there's natural wind currents within these cells. So even though the air in the intertropical convergence zone at the Hadley cell on the surface of the Earth is moving in towards the equator and then rising up over the equatorial zone, right? The air is also moving in what I would call the trade winds, and it moves easterly. It has a natural curvature to the east, right? The subtropic high, where the air is sinking, the air once again curves because of the Coriolis effect, and when it curves, it turns, but it turns so that it blows westerly. So within my Ferrel cell, winds move to the west, westerly winds. And then finally, in my polar cell zones, both north and south poles, you'll notice the air on the surface, this is the surface air, moves easterly. So, to review, Hadley cells, the air moves eastward, and we call them the easterly trade winds. In the Ferrel cell, the air on the surface moves westerly, and in the polar cell, the air moves easterly again. And these are all things that you're going to have to commit to memory. They're important. This also means that we have natural prevailing winds in these locations. For example, we expect the wind, unless you're in a local climate zone, like that sea breeze, land breeze, mountain breeze, valley breeze, unless you're in those local climate zones where there's specific breezes moving on a microscale that overrides the mesoscale, we have natural mesoscale wind conditions that will persist. And us living around 40 degrees north latitude, if you live close to the coast, you can expect sea breeze, land breeze, but if you live inland, you can expect westerly winds. So for example, people live on the inner parts of New York State, along the other side, right, along the western side of New York State, they get all their wind and weather conditions coming off the Great Lakes, which has lake effect snow. They're expecting westerlies. Where for us in Westchester, we're in a microclimate, and a lot of our air conditions are adherent to the Atlantic Ocean because of our proximity to the coast. So once again, I'm going to skip through these cells. These are just terms, and I'll come right back after I pause. All right, I'm going to pick up with the natural shifting of these high and low pressure cells, which just shows you that these natural cell cycles do move northward and southward dependent on where the sun is most directly hitting the Earth's surface. So this goes all the way back to when we talked about Earth-Sun geometry and the natural Earth-Sun angles, and you can see that that shift between the north and southern poles moves the high and low pressures northward and southward depending on seasons. And now they're